Okay, in the last video, we saw that by adding a compensation capacitor to the amplifier, we could potentially make the amplifier more stable. And we determined that the best place to add a compensation capacitor in this two-stage amplifier was between the output node of the first stage and the output node of the second stage. And the reason for this is that if we put the capacitor here, it gets the Miller effect due to the inverting gain from transistor Q6. It also sees a relatively high impedance, which will allow us to move the pole in to a very low frequency, which is ideal for our operational amplifier. After compensation, we knew that the poles and zeros were at the following locations. Omega P1 was approximately equal to 1 over GM2 times R2 times R1 times CC. Now this GM2 times R2 term is actually the gain of the second stage, and that is due to the Miller effect. Omega P2 was approximately equal to GM2 times CC divided by C1, C2 plus CC times C1 plus C2, where C1 and C2 are the capacitances at nodes 1 and 2. In other words, the capacitances of the first stage and the second stage. Finally, we also noted that the inclusion of this capacitor gave us a zero that was equal to GM2 over CC. And this is a left half plane zero. Now we approximated the second pole frequency as being equal to GM2 divided by CL, and this assumes that at our output we're driving some load capacitance. All right, so let's go back to our model of our operational amplifier. We treat the first stage as if it's a GM, and this makes sense because it has a relatively high impedance. Now that GM is driving the output resistance of the first stage, which in this case is RO1 in parallel with RO3 as drawn. And we've added our compensation capacitor here. Now, in the midband, the compensation capacitor we can treat as if it's a short. So at midband frequencies, we're going to short the compensation capacitor, and now we can calculate our voltage, our output voltage. V out is equal to GM1 times Vn times the impedance that we see at the internal node, node I. This is 1 over GM6 due to the diode connection, in parallel with RO1 and parallel with RO3. We can write that our voltage gain in the midband is equal to approximately big GM1 over GM6, assuming that GM6 is a much smaller impedance than both RO1 and RO3. This is in turn equal to minus little GM1 over little GM7. So if we're going to plot a Bode plot of the frequency response, or the magnitude response of this gain, it would look something like this. We'd have the intrinsic gain at low frequencies, A sub 0. We'd see a one-pole roll-off, and this is due to the dominant pole. So this would start at omega P1. Then we'd hit our zero frequency, omega Z1. We'd have a gain of minus GM1 over GM6. Sorry, I noted here that I wrote the wrong subscript. It should be GM6 up here in that equation. Finally, we would get to another pole frequency, omega P2, and we'd roll off at 20 dBs per decade. So we have an issue here. The right half plane 0 is causing a negative phase shift, which is the same direction of phase shift that the left half plane poles cause. And depending upon the sizing of our transistors, the GMs might be such that the gain is slightly greater than 1. Now, we know that having excess phase shift in excess of 180 degrees is a problem for us. This reduces our phase margin, and we don't want to have small phase margin, so we need to do something to get rid of this right half plane zero. So in the next video, we're going to look at some solutions to getting rid of this right half plane zero.